All right, the last section, Module 8, 8.7, as far as I know. I don't know if they're adding any more to this. I don't know. I don't think they are, but polynomial functions. Now, this is going to cover a lot of different things. So I can already tell it's probably going to be a pretty long video, but it is a very important section overall. There's so much in here, but it's so many important things that what we've been doing up to this point means so much for. So if you've done pretty well on everything up to this point, you've GCF, grouping, the trinomials, factoring, if you feel like you're an expert at factoring, this won't be too much more difficult for you, because factoring is obviously the key to a lot of this. But let's just go ahead and let's get into it. So a polynomial function. Okay, you guys have seen polynomial functions. You know, x squared plus 3x plus 2. You know what a polynomial function looks like. It's got those exponents, those variables, those numbers, all a bunch of random stuff, right? What we haven't really talked about is the zeros of a polynomial function. So let me read this to you real quick. All right, when studying linear functions, one of the most important key features addressed was the y-intercept. It anchors the linear function to the y-axis, and the x-coordinate of the y-intercept is 0. Zeros of polynomial functions have a similar level of importance. Instead of lying on the y-axis, zeros of the function lie on the x-axis. So it's anchoring to the x-axis instead of the y. Now, what is the y-coordinate of any point on the x-axis? The y-coordinate for any point on the x-axis would be 0, which is hence the name 0. Finding these zeros will require you to apply the factoring skills you have been mastering. So let me use a graph to demonstrate, right? So let me draw some random, polynomial function. Like this, like this, like this. Here you go, okay? Normally, we've been looking at the y-intercept. That's been a very important thing that we've done in the past, especially with linear functions, is the y-intercept. So that's where the function crosses, the y-axis. So in this case, right there. But what we're going to be focusing on here is zeros. Zeros is the point on the x-axis. Those are going to be the key points here. Those points are known as the zeros, okay? There's some other names for them. People will call them the solutions a lot of times. There's more that I'm blanking on right now, but for now, we'll call them the zeros. And the reason they're called zeros is simply because the y value for each point is 0. So like this point here would be -7, 0. This point would be -1, 0. And then this point would be 5, 0. So the y-intercept 0 in all of them. Kind of that's the reason we call them zeros. But it is those points. It's those x-intercept points. -7, 0, -1, 0, 5, 0. Right? So that's what we're talking about, is where your function, your polynomial, will cross the x-axis. Now, looking at a graph is one thing, but what if we try to find those values without graphing it, right? How do we do that? And the key is going to be through factoring. So here's an example that they show of x squared, f of x equals x squared plus 4x plus 3. So let me do that over here. We have f of x equals x squared plus 4x plus 3. Now, if we are asked to find the zeros, also sometimes it will ask find the solutions or something. They want us to find those x-intercepts. And the way that you do it is through factoring. So we are going to have to factor this polynomial of x squared plus 4x plus 3. Now, given that there are 3 terms in that polynomial, we are going to have to use our product and sum method, which I called it once in a previous video. Essentially, what we need to do for a trinomial like this is we need to figure out which 2 numbers multiply to make the a times c value, which in this case, a is going to be 1 for 1x squared, and c is going to be 3. So 1 times 3 is going to be 3. So I need 2 numbers that multiply to 3, and the same 2 numbers that are going to add up to equal 4. So what 2 numbers will multiply to 3, but also together add to 4? And this should be a simple one, right? 3 times 1 is going to equal 3, and 3 plus 1 is going to equal 4. So my two numbers are 3 and 1. So remember, what we do with those is we convert them into x terms to replace the middle x term. So the polynomial was x squared plus 4x plus 3, but we're going to replace this term here in the middle with these two instead. So since they're both a positive 3 and a positive 1, we'll put plus signs, so plus 3x plus 1x. Let me maybe make that a little bit larger. So plus 3x plus 1x, and then don't forget that plus 3 at the end. So the 4x that used to be there is now gone and replaced with the 3x and the 1x from the puzzle. So you factor by grouping. So factor by grouping, the first group has an x in common, so we'll factor that x out, and that leaves us with x plus 3 left in the parentheses. And the second group doesn't really have anything to factor out except for maybe a 1, so you can consider the 1 being factored out and leaving you still with x plus 3. So our final factored form, we've got the inside factor that matches of x plus 3, that's our inside part, and our outside factors of x plus 1. And if you might remember in a previous video, I think it was 8.03 video, maybe it was 8.05, the shortcut here, where if the a was equal to 1, that these values from your puzzle, the 3 and the 1, would end up being the values in the binomials, the 3 and the 1, x plus 3 and x plus 1. But we're not done yet, right? We haven't actually found the x-intercepts. So the zeros are what makes these two binomials equal 0. So essentially, take your factors, so in this, each of them one at a time, and set them equal to 0, and then solve for x. So one of the factors we have is x plus 3, so we're going to take that and set it equal to 0. And the other one is x plus 1. So x plus 1, we're going to take that, set it equal to 0. And now all we have to do is just quickly solve for x. So the first one, you can subtract 3 here. And now you solved for x. X is equal to 0 minus 3, which is negative 3. So x equals negative 3. And the other one, you would subtract 1 to solve it. Cancel that out. We end up with x equal to negative 1. So 0 minus 1 is negative 1. So that tells me exactly where my zeros on my graph are. My zeros would be on the x-axis. I'd have it at negative 1. And on the x-axis, I'd also have it at negative 3. So those all would be where my two zeros are, the x-intercepts. Now, I haven't drawn the graph. The graph could look something like this, or maybe look something like this. We're not 100% sure, but we do know that it crosses the x-axis at negative 3 and negative 1. That's the key here. And so that's what you see. You can see they factored it in that example. You can see they've taken those factors, set them equal to 0, and they end up with x minus 1, or x equals negative 1, and x equals negative 3. So you've got several examples here that we can try. So let's do this first one. Find the zeros of that. We have x to the third plus x squared. Let's see here. How does this work? Oops, it's not what I wanted. Can I delete them? Okay, well, that kind of worked. Not really as much as I was hoping, but it's all right. So let's try the next example here. X to the third plus x squared. Oops, need a color back. X to the third plus x squared. Minus 4x minus 4. Minus 4x minus 4. Now I notice there are 4 terms here. So when I see those 4 terms, I think immediately of factor by grouping. I notice right away that there is no GCF for all 4. So I'll just go ahead and jump straight into factor. This is getting very glitchy. Factor by grouping. So we'll group together the first and last 2. So the first group has x squared that we can factor out. And that leaves us inside the parentheses, that leaves us with x plus 1. A lot of times people think this becomes 0. X squared divided by x squared all cancels out and becomes 0. But it's not, because x squared divided by x squared is 1. Anything divided by itself would be 1, not 0, because you're doing division, not subtraction. It's very key to remember that. The second group has a negative 4 that we can factor out. So we'll factor out that. And that leaves us in parentheses with a positive x and plus 1 again, since a negative 4 divided by a negative 4 is the positive 1. So I've got two groups. I've got x plus 1 as my inside group, and I have the x squared minus 4 as my outside group. Now, some of you might think, oh, hey, look, we're done. But some of you might realize that there is still a little more here. And if you watch the 8.6 video, you'll know exactly what that is. In this case, we have x squared minus 4 is still factorable. It's factorable by the difference of squares. So the square root of each of these would be x and 2, meaning that we would pair them together as x plus 2, x minus 2. So if you saw 8.6 video, you know what that is. Don't forget, though, the x plus 1 is still there, still very, very relevant as part of our answer. So we have this as our final answer. Well, not our final answer, but our final factored form. But remember, to find the zeros, we take each of them and we set them all equal to 0. So we'll take x plus 1, set it equal to 0. We'll take x plus 2, and we'll set it equal to 0. And then we'll take x minus 2 and set it equal to 0. And we solve each of them. Now, they're pretty simple to solve. You know, you subtract 1, you end up with x equals negative 1. In this case, you subtract 2, you end up with x equals negative 2. And the last one, you would add 2, since it's already minus, and you end up with x equal to positive 2. So these are your zeros here, and you can put them on the graph. They would be at negative 1 on the x-axis, at negative 2 on the x-axis, and at positive 2 on the x-axis. So your polynomial will cross the x-axis in those places. It could look something like this, you know, and in the crossing there, we don't know exactly how it looks, but we do know for a fact that it crosses at negative 2, at negative 1, and at positive 2, because that's the results we ended up with here. So it comes down to factoring. If you can factor, then the only new thing at all is just setting each factor equal to 0. And how hard is that, honestly? Because you just take the equal to 0, you solve it in a matter of one step, and you've got your answer. So if you already know how to factor, then this is the only thing that's new in this part of the video, where you just set them equal to 0 when you solve. And like I said, that's not that difficult. So make sure you're really good at factoring. The next example, this is a very good one. Solve 4 equals 3x squared minus 11x. How are we going to do that? So let me, again, erase this so that I have the graph that I can still use. So we have 4 equal to, what was it, 3x squared plus 11x, minus 11x, minus 11x. Okay. Now, how are we going to solve this? Now, what we need to do is we actually need to make sure that this quadratic ends up equal to 0 instead of equal to 4. So how do we do that? Well, simple. We just have to get rid of the 4. We have to move it from this side, subtract it on this side, subtract it on this side to have it moved over. So that leaves you with 0 equal to 3x squared minus 11x minus 4 now. So the 4 simply moved from here to here. And you'll notice it doesn't combine with the 3x squared or the 11x. It's just simply added on to the end. And the reason for that is because it's not like terms with any of that stuff. It's not an x squared term, so it doesn't combine with the 3x squared. It's not an x term, so it doesn't combine with the 11x. It's just a plain old 4, so it's just sitting there at the end being all plain and boring 4, okay? But now we have something factorable. So when we factor this, remember with the trinomial, we want to solve our puzzle. We have to find two numbers that multiply to equal the a times c value and the two numbers that add to equal the b value. Now in this case, our a and our c are 3 and negative 4. So when you multiply them together, 3 times negative 4, you end up with negative 12. So we're going to find two numbers that multiply to negative 12. Our b value here is negative 11. Okay. Now, one thing to notice is how close negative 12 and negative 11 are to each other. When they're like that, you want to think of the number times 1. So like a 12 times 1 in this case. So since 12 is negative, right, one number is going to have to be positive, the other is going to have to be negative, because a negative number times a positive number is going to equal a negative 12. So what's it going to be here? Is it negative 12 times positive 1? Or is it negative 1 times positive 12? Well, we have to pair that up with our 11 and find out. So if it's negative 12 times positive 1, negative 12 plus 1 is negative 11. So that works, right? If you had it the other way around, positive 12 and a negative 1, then this would actually be a positive 11 here, not a negative 11. So that wouldn't be correct. So it is got to be a negative 12 and a positive 1. So negative 12 and a positive 1. Now don't forget, the main reason we need to do that is because we need to convert these two into x terms to replace that original middle x term. So we have 3x squared. We had minus 11x minus 4, but we're replacing the minus 11x with the minus 12x plus 1x. So we continue by factor by grouping. So we're going to group the first two and the last two. Now the first group, both 3 and 12 can be divided by 3, and both terms have an x, so we're going to factor out 3x. Now that leaves you with a regular x minus 4. And in the second group, we already kind of have a regular x minus 4, so you can just factor out the 1. The 1's not going to change anything. It's still going to be x minus 4. But now we have our factors. We have the, oh, I didn't put this in blue. I wanted to put this in blue just to make it, color code match. Okay, here we go. So our inside group is x minus 4, so that's one factor. And our outside group is 3x plus 1. Now, you want to check to make sure nothing else is factorable, and in this case, nothing else is factorable. There is no difference of squares. There is no more GCF. These two here at the end are fully factored. Nothing else I can do. So remember, to find the zeros, you just have to take them and equal them to 0. So x minus 4 needs to equal 0, and we need to solve it. And 3x plus 1 has to equal 0, and we need to solve it. So the x minus 4 is an easy one. We would just add 4, and we end up with x equal to a positive 4. But for the next one, we have a little bit more work to do. We have to subtract the 1 first. That leaves you with 3x equal to negative 1. But you also have to get rid of the 3. Since it's being multiplied to x, you'll have to divide by 3, which means that x is going to equal a fraction. In this case, it's going to equal negative 1/3. Negative 1 divided by 3 is simply negative 1/3. So these are the two solutions. We have an x-intercept at 4 and at negative 1/3. So if we went to our graph, I don't know what the rest of the graph looks like, but I know crosses the x-axis at 4, and then negative 1/3 would probably be like right there, about a third of the way over. So something like right about here would be our second x-intercept. It would cross the x-axis there. And I don't know what the polynomial looks like. It could look like this, or it could be the other way around. But I know it crosses the x-axis through those points. That's what matters. So there's that problem. I'm sure they'll show you the work, and you can see, yep, negative 1/3, the 4, all that stuff, right? Example 3, let's try that one. X to the third minus 16x. Again, let me just erase all this real quick. Okay, so x to the third minus 16x. Now, in this case, does it say f of x? What does it say? Yeah, it says f of x. In this case, I see the two terms, and I think difference of squares immediately. However, what I do notice right away is, x to the third is not a perfect square because only even numbers would work as perfect square, even exponents. But what I do notice is that between these two terms, there is a GCF. Both terms have an x in it, and I should be able to factor that x out. So if I factor that x out, then I've got x squared minus 16 in the parentheses. And now, look, that is factorable through difference of squares again. So when you take the square root of each term, the square root of x squared is x Square root of 16 is 4. So we just pair them together. We have x plus 4 and x minus 4. But don't forget, the x that we pulled out is still pulled out. It's still chilling out here. So you have this as your factored form. Now don't forget, we still have to set each part equal to 0. So you know the drill. We'll take x plus 4 equal to 0. That's this one. We'll take the x minus 4 equal to 0. But also, we have to account for the x here. So that x, that solo x, also has to be set equal to 0. And when you solve all of these, well, this one's technically already solved since x equals 0. But the other ones, you would subtract 4 from. This becomes x equals negative 4. And the last one, we have to add the 4. We end up with x equal to positive 4. So we have 3 x-intercepts. One at negative 4, one at positive 4, and one at 0. So one at negative 4, one at positive 4, and one at 0. So again, I don't know the shape of the polynomial, but I know it crosses the x-axis in those 3 spots. All right, let's move on. Now, here's what we were trying to do, right? Using the zeros to make a sketch of the graph. So they have an example here. They've got x to the third plus 3x squared minus x minus 3. They have x to the third plus 3x squared minus x minus 3, right? And they went ahead and factored this to find the zeros. So when you factor this, you would factor by grouping. I'm just going to kind of quickly run through the factoring here. So factor out x squared. That leaves us with x plus 3. The second one, we can factor out a negative 1. That factors in the x plus 3. So we have the x plus 3 is the inside. The x squared minus 1 is the outside. That is still factorable by difference of squares. Square root of that is x. Square root of that is 1. So we pair them. X plus 1, x minus 1. But don't forget to bring the x plus 3 part down. So I factored it. I did it quickly, I know, but we've been factoring this a lot. So if you still have issues factoring it, you need to go back and practice that some more. But remember, let's find the zeros. Each of these has to equal 0. So x plus 3 equal to 0, x plus 1 equal to 0, and x minus 1 equal to 0. And just to quickly solve them, this would be x equals negative 3, x equals negative 1, and x equals positive 1. So we have these 3 x-intercepts, one at negative 3, one at negative 1, and one at positive 1. And they've already got those on that graph. You can see that graph there. They also went ahead and found the y-intercept. Now, the y-intercept is actually very easy to find because you would just take your original, polynomial, right? X to the third plus 3x squared minus x minus 3. And to find the y-intercept, all you got to do is just plug 0 in to every single x. So 0 to the third plus 3 times 0 squared minus 0 minus 3. Which obviously this would be 0 plus 0 minus 3 means that minus 3 is the y-intercept because 0 plus 0 minus 3 is just going to be negative 3. So the y-intercept would be a negative 3. So I don't know the shape of my graph, but I know it goes through all of those points. Now here's the tricky part that you need to kind of make a note of is end behavior. Okay, there's the y-intercept. There you go. Got the point already, right? The end behavior. Okay, so take a screenshot, take a picture, whatever you got to do here of this little chart to describe end behavior. So we're going to come back to this problem here in a second and graph it. Before I do, let me discuss quickly what the end behavior is all about. So an even polynomial is something that has an even exponent. So for example, any polynomial that has the x squared or the x to the fourth or the x to the sixth, okay? Anything that has an even number exponent. The odd polynomials would be obviously anything that has the odd exponents, like x to the third or x to the 5th, or x to the 7th, etc., right? So even odd. And what we're talking about is talking about just the first or the highest. Usually it's the first, but the highest exponent term. So in our example here, the highest exponent term was the x to the 3rd, making this an odd polynomial, okay? Now, the other thing to point out is the positive and negative, okay? If it's a positive odd polynomial, okay, then the left side points downwards, the right side points upwards. So for example, a graph of that would look something like this. Right? You can see the left side's going down, the right side is going up. That's how a positive odd polynomial would behave on the ends. If, let's say we had a negative odd polynomial, it would be the opposite. It'd be up on the left and then down on the right. So an example of a graph like that is it would go something this way. It'd go up on the left side, but down on the right side. So that would be a negative odd polynomial. If you have even polynomials, let's start with a positive even polynomial. A positive even would have both ends go upwards. So an example would be something like this, where the left side and the right side are both pointing upwards. And then, of course, a negative even will be exactly the opposite. You could probably tell where this is going. A negative even polynomial would both be going down on both sides. So something like that, where the left side is pointing down and the right side is pointing down. So just a quick example. A positive odd would be, you know, like x to the 3rd or x to the 5th or x to the 7th. A negative odd would mean that it starts with a negative x to the 3rd, a negative x to the 5th, or negative x to the 7th. Obviously, you could have other numbers. You know, you could have a negative 2x to the 7th or a negative 9x to the 5th. But notice, the exponent is odd and the number in front is negative. Okay, positive odd could be the same way. You could have like 5x to the 3rd or like 10x to the 7th or 10x to the 5th, right? You have the odd exponent and a positive number in front. So a positive number in front, odd exponent has this end behavior. A negative number out front with an odd exponent has this behavior. Positive even, so even are going to be, of course, like x to the 2nd or x to the 4th or x to the 10th polynomials. And then positive, meaning a positive in front. So it could be a positive x squared, or it could be a positive 2x squared, or it could be a 7x to the 4th, or it doesn't matter what number it is. It could be an even or odd here. It's just a positive number with an even exponent. Has that end behavior. And then, of course, negative. So it could be a negative. It could be an even exponent, like x to the 2nd, x to the 6th, x to the 8th, but a negative in front. So a negative x squared, or a negative 3x to the 6th, or negative 9x to the 8th, right? If it's negative out front and then an even exponent, it has this end behavior. So you've got 4 categories to sort of memorize, okay? Kind of how their ends go. So when you look at this polynomial that we are given, right, its highest exponent is 3, so we know it's odd. And it's a positive since there is no negative, right? So it's a positive odd function, meaning its end behavior follows down on the left and up on the right. So if I were to quickly make a sketch of this, I know that on the left side it's pointing downwards, on the right side it's pointing upwards. So, and it has to go through all those points. So we'll have to go up through here, come back down through this one, cross the y-axis, come back up through that point, and then it can carry on. So you can see I've made my polynomial so it crosses all those points and the end behavior goes the correct directions, okay? So there's a lot to remember here. It's one of those things you kind of really want to chart and have next to you, or just kind of memorize, study it again and again, especially, all the end behavior stuff. Let's try another example because obviously one is a lot. There's too much to kind of do in just one problem. So let's see if we can try and make another problem. So here's their example. They got another one. They have x to the third minus x squared minus 16x plus 16. Trying to zoom in here. Okay, so they have x to the third, what is it? Minus x squared plus 16x. No, is it minus 16x? Minus 16x plus 16. So again, we're going to factor this by grouping. We have to factor it first to find the zeros, remember, so don't forget about that. So I'm just going to go quickly through the factoring. So this first group has the x squared, leaving x minus 1. The second group has a negative 16. And that's going to leave us with an x minus 1 as well. So we have the inside x minus 1, then the outside x squared minus 16. Notice the difference of squares here can still be factored. Square root is x, square root is 4. So pair them. It's going to be x plus 4, x minus 4. And then don't forget the x minus 1 is still here as well. So when you set each of these equal to 0, just to quickly do it, x minus 1 equal to 0, x plus 4 equal to 0, and then x minus 4 equal to 0. We end up with x equal to positive 1, x equal to negative 4, x equal to positive 4. So I know its x-intercepts are at 1, negative 4, and positive 4. So 1, negative 4, and positive 4. I know the x-intercepts are there. Now the y-intercept is easy because remember you just have to plug 0 into all the x's. So 0 to the third minus 0 squared minus 16 times 0 plus 16. So obviously that's 0, 0, 0. Means the y-intercept is going to be at positive 16, which I can't really fit on here, but I'll imagine it works, right? Plus 16, positive 16 would be like way up there. Oops, didn't want to move that. Okay. So the last thing I'm going to look at is its end behavior. Now noticing my polynomial, remember it was x to the third minus x squared minus 16x plus 16. The highest exponent is a 3, so it's an odd polynomial, and it's a positive, since it's a positive x to the third. So a positive odd. Now remember, positive odd goes down on the left and up on the right. So down on the left, up on the right. So when we do that, it's going to have to go on my graph. It's going down on the left. It's going to have to go up through here. Obviously, it's got to go way up there to hit that y-intercept. Come skyrocketing back down. And I don't know where to turn around. We'll turn around here. Right? So something like that. It's just a real quick sketch going through all our points. We have the zeros, remember? 1, 4, negative 4 as we got. The y-intercept 16 as we got. We mentioned it was positive odd. So theirs obviously looks a little different than ours, but it goes, they had a better graph than us. But they kind of made it work. So very tricky. But, we are just kind of making a sketch of it at the end of the day. So don't worry about it too much. Okay. Now, this is a whole other bit of stuff here. Axis of symmetry. So axis of symmetry is going to be good for quadratics. Things with just x squareds, not any x to the thirds or anything like that. Just x squareds, okay? Not x to the fourths, x to the fifths, just x squareds. But it has a formula. It's a very useful formula. It's seen on the screen there. It's x equals negative b over 2a. There's an example clearly worked out here, but I'll go ahead and kind of explain it. Let me just go ahead and snip it actually, and we'll just go with that. So in this equation, our A value is 2, our B value is 4, and our C value is negative 6. So if we just follow this formula, x is going to equal negative B value. The B value there is 4, so the 4 is going to be on top. Then on the bottom, it's going to be 2 times A. The A value is 2 as well, so it'll be 2 times 2. So when I evaluate this, this is going to be negative 4. 2 times 2 on bottom is going to be 4. And 4 divided by 4 is 1, so this essentially just becomes negative 1. So x equals negative 1 is our axis of symmetry. Now, what that means, and you can see they've got that same work and everything shown here. What that means is when you look at a graph, okay, look at a graph, x equals negative 1 is right here. There's going to be a line that goes vertically through that negative 1. So I'm doing a very bad job making a straight line, but you get the idea. That's going to be what splits the graph right in half. Okay, so if you look at the graph that they provide, oh wait, I gotta do that, go back to this. No, this one. Right, look at the graph. Right, you see that dotted red line at negative 1 on the x-axis, it splits the graph directly in half. Right down the middle. It's called the axis of symmetry for a reason, because it creates that symmetrical, part of the graph. It's split into 2 even symmetrical halves. It's halfway down the middle. If that makes sense. Hopefully it does. Okay. So axis of symmetry, pretty simple. It's a very short formula, just negative b over 2a. But it's going to come a little bit more in handy on the next slide with vertex point. So vertex point is based on the axis of symmetry. Now, if you look at our graph here, let me again snip this. Right? Remember the axis of symmetry that goes right down the middle. Well, guess what? If it goes right down the middle, then it's going to go straight through the vertex here at the very bottom of the graph. Because the vertex is where it gets split in half, right? So the fact that, we know that the axis of symmetry has to go through this vertex. It has to touch that vertex because the axis of symmetry is not going to be skewed to the left, right? It's always going to go straight through the middle, which means it's always going to go through that vertex. Now, the reason that's useful is because now we know if the axis of symmetry is at negative 1, then I know my vertex is also on that line, x equals negative 1. The vertex has to be on that axis of symmetry at negative 1. So we're going to take that information and use it to help us find exactly where the vertex is. So if does it have the function itself? It doesn't even have the function. Let me go back a slide real quick to see if I have the actual equation of our function. There you go. So 2x squared plus 4x minus 6. So let me go back to this. You have 2x squared plus 4x minus 6. So remember, we already went ahead and did the axis of symmetry formula, right? Negative b over 2a. Right? It was negative 4 over 2 times 2. It simplifies to negative 4 over 4, which simplified negative 1. So we knew the axis of symmetry was at negative 1. Well, now if we know the axis of symmetry is at negative 1, then we can plug this in to this equation to find out where the vertex is. So that means plugging negative 1 in to the x value of the equation. So 2 times negative 1 squared plus 4 times negative 1 minus 6. So since the axis of symmetry is at negative 1, I can plug that in to find out where the y value of that vertex is. So now when I calculate this, remember exponents come first. So negative 1 squared is a positive 1. 2 times positive 1 would be 2. 4 times negative 1 would be negative 4. And then minus 6. So if I put all of this together, 2 minus 4 minus 6 would be 2 minus 4 is, let's do one thing at a time. 2 minus 4 is negative 2. Negative 2 minus 6 would be negative 8. So that means my vertex would be at negative 1, negative 8. Because negative 1 was where the axis of symmetry was, and negative 8 is the y value I got out when I plugged negative 1 in. So my graph would have its vertex at -1, -8. And we didn't do this as part of the problem, but it's something that you should still be able to do, which is factor this and find the zeros. So if you actually factored this, you can factor a GCF out first. Then you would factor that trinomial in the middle. So we would have two numbers that multiply to equal -3, and then two numbers that add to make 2. Those two numbers would be 3 and -1. Since here the a value is 1, I'm just going to cut to the chase, and the factors would be x plus 3, x minus 1. So, oops. If you take each of them equal to 0, obviously 2 doesn't equal 0 at all, so it's kind of irrelevant here. But the x plus 3 equal to 0, the x minus 1 equal to 0, you would end up with x equal -3 and x equal +1. So these would be the x-intercepts at -3 and +1. So using no calculator at all, you can find the axis of symmetry using the formula -b/2a. So we found that at -1. So this vertical line, -1. We found the vertex by plugging in the -1. So we knew it would be at -1/8, the vertex. And we can factor the polynomial to find its zeros. It crosses the x-axis at -3 and 1. So now we can kind of sketch it all together to make our graph as accurate as we can. So there's a lot of pieces of a graph that we can find. We can find the zeros through factoring. We can find the vertex by using the axis symmetry formula and then, plugging that in. So the axis symmetry formula gives you the x value, and then the y value you get from plugging that value in. And you can also learn end behavior, although we didn't have to do it too much on this one. We had it, the biggest exponent was even, and the first number here was positive. So a positive even graph would go up and up. So that's why you can see the left side goes up and the right side goes up. So you can graph this whole thing through all these, by finding all these different pieces. It's a lot. Yes, I give you that. It is a lot, but it is neat that we are able to do all of it, though. Okay. There are some practice problems here. I guess I'll maybe do one on each of these. You can stop the video here if you feel good, or if you want to practice these on your own, practice these for sure, but I'll walk you through a couple of them. So let's do this first one. We have -3x to the third. I'm just going to snip this instead of writing it all down again. So we're going to factor this by grouping because there's 4 terms. But before I do that, let's see if there's a GCF. Is there a GCF for all 4 terms? And I think there is. I think every term is divisible by 3. And since this first term is negative, I'm going to actually factor a -3 out of every term. So the -3 can come out, which will mean I'll have x to the third plus 5x squared minus 4x, and then 60 divided by 3 is 20, so -20. So I've got, let me rewrite this. I got -3 on the outside, x to the third plus 5x squared minus 4x minus 20. So now I'm going to factor by grouping. So group the first 2 terms here together and the last 2 terms here together. So these I can factor out x squared. And that's going to leave me on the inside with just x plus 5. And with the second group, I can factor out a -4. So I'll factor out -4. And on the inside, that would leave me with x plus 5 again. So we have the inside part matches. It's x plus 5. And then the outside part is x squared minus 4. X squared minus 4. So we've got that factored. Now we do have to notice that this here is still factorable again. So we have the difference of squares. So difference of squares, that's going to be factored, square root of that is x, square root of this is 2. So that pairs up as x plus 2x minus 2 to factor it out. And of course, don't forget the x plus 5, still part of our answer. So this is our fully factored form. X plus 5, x plus 2, x minus 2. I totally forgot, by the way. Oops. I got rid of it. Did I get rid of it? I got rid of it. The -3 is still on the outside. I totally forgot about that. It's very important that you remember that. But then you set everything equal to 0. So x minus 2 equal to 0, x plus 2 equal to 0, x plus 5 equal to 0. And you get those results of -5, -2, and +2. So yeah, I kind of messed that up. I kind of went through it a little too quickly there. My bad. But you get the idea of how to factor it. So here, this one says solve the quadratic by factoring. So here we have x squared minus 12x equals 0. So if we factor this, the first thing, again, you want to focus on this, because equals 0 is what it's supposed to be, right? That's not really part of the factoring. We're factoring that 2x squared minus 12x. So for factoring the 2x squared minus 12x, first thing I'm going to notice is a GCF. Both terms here can be divided by 2. Both terms have an x in it, so I'm going to factor that out. So if I factor 2x out, that leaves me x minus 6. And so now the last part is, remember to set each of these equal to 0. So you got two groups. You've got the 2x on the outside that has to be set equal to 0. And you have the x minus 6 as well that needs to be equal to 0. So when you solve this, simply divide by 2. That one's not going to change. X is still going to equal 0. Since 0 divided by 2 would still be 0. But for this one, we'll add 6. And then we get x equal to 6. So we get 0 and 6 as our two zeros. Okay. There are more practice problems, remember, so hit next, and do more of them, but I'm just going to do one of each. Here, let's do number 2 because it's got that negative. Or should we do number 3? We can do number 3, right? Let's do this one. So with this one, there is a GCF overall. Every term here can be divided by 2, but a -2. So if you divide everything here by a -2, I'm going to have to use a different color as well. So what color would be good? Blue, maybe? Oops. Let's use a darker color. Okay, so -2, -2, -2, -2. Everything can be divided by a -2, which means with that out, we would have x to the third plus 2x squared minus 16x, and then minus 32. So we continue to factor this by grouping. We would group the first two terms together and the last two terms together. I am going to need some more colors here. Let's go with, it's going to look so bad. Let's go with red. So first group has an x squared that we can factor out. So x squared can be factored out. That's going to leave us with x plus 2 inside. Can I use white? That's sort of better. I don't know. You guys, I apologize if your eyes hurt. It's my fault. Here we can divide by -16, bring the -16 out. And in parentheses, we're going to get the same thing. We're going to get the x plus 2 again. Oof, this is so hard to look at. I'm so sorry. All right. But our final answer, well, not really, but our next factored form, we would have the inside part is x plus 2, and the outside part is x squared minus 16. So this can still be factored. Square root is x and 4, so it can be factored into x plus 4, x minus 4, and the x plus 2 as well. We also have the -2 that came out on the outside. It's still there, but that's kind of irrelevant since it doesn't have an x on it. Because -2 with no x on it is pretty much useless. You really only focus on the things with x. So you have x plus 2 you need to solve equal to 0. You have x plus 4 equal to 0, and then the x minus 4 equal to 0. So each one of those. And when you solve it, you're going to end up with x equal to -2, x equal to -4, and x equal to +4 as your final answer, I think. Is that what the question wanted? Oh, it wants sketch the whole graph. Okay. So we know the zeros would be through those points, -2, -4, and 4. Let me go back to this graph. So it would go through -2, 4, and -4. I know this is the x-axis. I also know the y-intercept would be found by just plugging 0 into the x value here in the beginning. So if I plug 0 into x, this would be 0 to the third, 0 squared, 32 times 0. All these become 0, and then 64 ends up being the y-intercept. Obviously, I can't graph 64, but it's going to be way up there, okay? And then the last thing, I guess, would be end behavior. So since this polynomial is negative and odd, a negative odd function would be up on the left and down on the right, based on the chart we saw earlier. So if it goes up on the left and down on the right, then this polynomial would look something like, again, I'm just making a quick sketch. It has to go way up there. So way up there and back down, it looks something kind of like this. Tough to do, but you're finding the x-intercepts, you're finding the y-intercept, and then just following the end behavior. So 3 things, okay? X-intercepts, this is done through factoring. The y-intercept, which is simply done by plugging in 0. And then the end behavior, which end behavior you don't have to do any math for. You just have to kind of pull it out of the polynomial. You have to look to see if it's positive and odd or positive and even, stuff like that. So it's really just based on the first term. It's a negative, it's an odd exponent, so it's a negative odd function. That tells you your end behavior. You follow those things, and you can get pretty much a really terrible sketch of a graph, but one that's kind of works. Okay, so there you go. Obviously, they've got a bigger scale, but it all works out for them. And I think, yes, I think there's a few more practice problems, but I think you guys can kind of handle it. So this one says, determine if the parabola opens up or down. Well, given the fact that this is a positive x squared tells me it's going to open up. So that's going to be, if it's a positive x squared, the parabola opens upwards like this. If it's a negative x squared, it's going to go downwards like this. Because remember, a positive even function, both go up. But if it's a negative even function, both go down. So it is going to open upwards since it's a positive even function. It'll open like this. It wants you to find the vertex and sort of, I guess, graph it. So if we were to graph this, right, I'm going to go back and put it on this chart since I have it. Gonna have to excuse the lagginess here. So what is our function? Our function is x squared minus 2x plus 3. X squared minus 2x plus 3. So just again, we know it's positive even because the first term here is it's a positive x squared and it's 2 is an even number. So it's going to, both ends are going to go up. We know that much. Now we want to find the zeros of it, so let's do that first. So we have to factor this. So to factor it, it's a trinomial, so we need to find 2 numbers that multiply to a times c, same 2 numbers that add up to b. So in this case, a is 1 and b is 3, so 1 times 3 makes this value 3. And my b value is -2, so I need to find 2 numbers that multiply to 3 but add to -2. In this case, it's going to be a -3 times a +1. -3 plus 1 gets you -2. So the 2 values are -3 and 1. And to use my shortcut, remember, since a is equal to 1, this only applies when a is equal to 1. This is going to be in my binomials. So my binomials will be x minus 3 and x plus 1. So what that tells me is if I set each of those equal to 0, x minus 3 equal to 0 and x plus 1 equal to 0, and I solve it, I get x equal to a positive 3 and x equal to a negative 1. Adding 3 to both sides here gets you positive 3. Subtracting 1 on both sides there gets you to negative 1. So I know my x-intercepts are going to be at 3 and negative 1. I can also find the y-intercept by plugging the 0 into the x. So if I plug 0 in for x, I get 0 squared minus 2 times 0 plus 3. So that's 0 minus 0 plus 3 means that the y-intercept is equal to 3. Wait, that doesn't seem right. Did I do that right? Oh. Yeah, wait, is it supposed to be positive 3? Did I write this down wrong? I think I just did something wrong. Hold on, let me go back. This is what happens when you make a really long video. It's a positive 3, right? Not a negative 3, so I messed that up. So two numbers that multiplied equal positive 3 and adds equal a negative 2. Now, I don't think that's actually possible because the only numbers that I could think of would be a negative 3 and a negative 1, but that doesn't add up to negative 2. Obviously, a positive 3 and a positive 1. This actually isn't factorable. So you're not going to find, this won't actually have any x-intercepts at all. So no x-intercepts. But we can still find its vertex. So my fault, I assumed that there was a negative 3 instead of a positive 3 at the end, and that was my mistake. But end behavior is still going to be the same. It won't have any x-intercepts, so no x-intercepts. But its vertex. Let's find its vertex. So follow the formula, negative b over 2a. So b is negative 2, which means if you plug in negative 2, that top part's actually going to be a positive 2 in the next step, but we'll save it for later. 2 times a is 1. So this will be a positive 2, and 2 times 1 is a positive 2, which means 2 divided by 2 is 1. So my axis of symmetry will be at 1. Now to find the vertex, I have to plug the 1 into x. So this would be 1 squared minus 2 times 1 plus 3. So this would be 1 minus 2 plus 3. 1 squared is 1. Negative 2 times 1 is negative 2. And then plus 3. So this ends up being, if you combine all these together, that equals 2. 1 minus 2 is negative 1. Negative 1 plus 3 is 2. So the vertex is at 1, 2, because the 1 was the axis of symmetry, and 2 was the y value we got from plugging it in. So the vertex is at 1, 2, which is here. And since it goes up and up, and behavior on the left goes up, and behavior on the right goes up, and we have that. And it has no x-intercepts because this was not factorable. So it doesn't actually hit the x-axis at all. Very interesting, actually. So that's kind of what this question was asking for. So it is tricky. It even fooled me, right? So sometimes if you're not focused, you're going to make mistakes. There's nothing wrong with that, but you have to be able to be like me in the sense that, hey, I've recognized something went wrong. Let me see if I can find a way to fix it. So be mindful of that. We're all going to have, those moments where we miss something. So there's the sketch that they made. Okay. So I think I've made this video long enough for you guys to kind of dissect it, rewatch it, do what you got to do. Good luck on this. If you have any questions at all about any of these practice problems or anything in general, just ask them in the discussions for us, please. We'll be happy to help you. But yeah, I'll leave you guys with that. And good luck on your quiz. Please remember you have multiple attempts. And we'll see you guys next week. Bye-bye.